Hello. In today's video, we're going to be looking at Lecture 10, pre-lecture. So we're going to be looking at the second lecture within Chapter 4. So in this one, we're going to look at, in this particular lecture, we're going to look at our different reaction types. Specifically, we're going to look at precipitation reactions, acid-base reactions, and redox reactions. So precipitation reaction is going to be one where we form a precipitant. So, for instance, we have the following reaction, 2Ki. So we have potassium iodide, which is soluble, reacting with lead nitrate, which is also soluble. And when they combine, you produce potassium nitrate, which is soluble, and then lead iodide, which is insoluble, which is indicated by that S. So if we have a double replacement reaction, with a solid product, this is a precipitation reaction. Okay, so determining what solid you're going to form is based on solubility of ionic compounds. Ionic compounds, for the most part, are soluble in water. But the solubility in general is an energetic thing. So we have to have favorable energies in order for us to have things be soluble. So we have to form electrostatic interactions between our solute particles and our solvent particles that are on par with the electrostatic interactions that are existed within the solute and solvent. So in the case of highly charged small ions, they are going to like other highly charged small ions more than they're going to like water. So they're not going to be as soluble as larger, lower charged ions. So just in general, if we have ionic compounds that are composed of ions that are small in size and highly charged, these are going to be less likely to be soluble in water. And that's because they're going to be very strong interaction between the ions that are hard to break, unlike larger ions that do not have as much interaction between the particles. So, as an example, something like calcium carbonate. These are both fairly small ions, and they're both have a large charge. So calcium carbonate is going to be an insoluble ionic compound, meaning when you throw it in water, it's not going to dissolve, or if you mix two aqueous substances that have calcium and carbonate in them, such as calcium chloride and sodium carbonate, when the calcium and the carbonate are mixed together in this way, they are the thing that is going to precipitate out. Because they're going to find each other and just latch on. Now, there are a set of rules for determining solubility of ionic compounds, not just large charge, insoluble, small charge, soluble. So we're going to go through this. Generally, we look at things that are always soluble or mostly soluble, and then things that are always insoluble or mostly insoluble. So we're going to first start looking at our soluble complexes. So this is going to include all nitrates and all acetate ions without exception. These both have small charges, and they're fairly bulky. So they are going to be, all salts that form with nitrate or acetate are going to be soluble. Then we have chlorine, bromine, and iodine. These are going to be all soluble except for a few exceptions. So these most are soluble. Our exclusions here are going to be compounds containing silver, mercury 2, and lead 2. So if you have silver chloride or lead 2 bromide, mercury 2 bromide or lead 2 iodide, those are all going to be insoluble complexes. And then our last example is sulfate. This has a high charge, but it's a very big polyatomic ion, so a lot of them are going to be soluble, but not all of them. So most are soluble, except those that are with silver, barium 2+, mercury 2, or lead 2. So this is in an additional one, the barium from the chlorine, bromine, and iodine. Like so. Okay. Next, we're going to look at insoluble complexes. In general, complexes that include S2- are insoluble. So all insoluble, except those containing those compounds containing our ammonium ion, all alkali metal cations, those that are with calcium 2+, strontium 2+, and barium 2+. Another one that is the same is OH-. So it has the same, let me just fix that real quick. It has the same exact exclusions. So S2- and OH- are both insoluble. All complexes are insoluble unless they contain ammonium ions, alkali metal cations, calcium 2+, strontium 2+, or barium 2+. Next one is going to be carbonate and phosphate. And you can see here our insoluble ones are going to be in general smaller more highly charged. So these are insoluble, except when in a compound with ammonium, or any alkali metal cation. As a note, our ammonium and alkali metal cations are also substances that are going to be always soluble. So, I should have added this here, but here we go. So if we have something with nitrate, acetate, ammonium, or alkali metal cations, those are all going to be soluble. Alright. So once we have a balanced precipitation reaction, we are going to call that balanced equation a molecular equation. So, as we were looking at earlier, 2Ki AQ plus lead 2 nitrate are going to combine to produce potassium nitrate and our insoluble complex lead iodide. So we call this a molecular equation where everything's together. This is what we've looked at so far. So these are our chemical equations we've looked at so far. But there are other equations we're going to look at in today's lecture, including a complete ionic equation and a net ionic equation. So our complete ionic equation is going to be one where we take anything that's in the aqueous state, any electrolyte, strong electrolyte in the aqueous state, and break it down into ions. So all strong electrolytes in the aqueous state are broken down into ions. So there, I don't know. That's going to include that one, and that one. It is not going to include this one because it's in the solid state. So let's try it out. We have 2K plus AQ plus 2I minus AQ plus lead 2 plus AQ plus 2NO3 minus AQ goes to 2K plus AQ plus 2NO3 minus AQ plus PbI2 solid. Okay. Now, as you hopefully notice, we did not break down the lead iodide because this is in the solid state. And additionally, we put our charges for all of our ions. Make sure these have charges. So make sure to include charges. Also, everything has a state. So you have to have charges and states in a complete ionic equation. You also have to have states in a precipitation reaction, or it makes no sense. Right, if you don't add states in a precipitation reaction, you have no idea what you're making. Okay, so you have to have charges and states when you're talking about a complete ionic equation. And when you are balancing this out, remember that any stoichiometric coefficient is going to be applied to every ion within the compound. And then remember that if you have a subscript, it's going to apply to the thing that it is directly connected to. So that's why we have a 2 nitrate here, 2K plus, 2I minus, and then again 2 over here and 2 over here. Okay, now this is a very long thing to write, so oftentimes the net ionic is the preferred equation to write. You guys will be writing all three: a molecular equation, a complete ionic equation, and a net ionic equation. And here we're going to remove anything that is the same on both sides. So our 2K plus, 2K plus, 2I minus, oops, no, not 2I minus, 2NO3 minus, 2NO3 minus. We do not, however, remove our iodine or our lead because they combine to produce our solid. So we're going to have 2I minus plus Pb2 plus combined to produce Pbi2 solid. That'd be our net ionic. And it's what's actually happening. Everything else is just hanging around and not doing anything. So our net ionic shows the actual reaction. As iodine ions in solution come into contact with lead ions in solution, they're going to combine together and form an insoluble complex, which will precipitate out of solution. Now, as a note, all other ions, those that are canceled out, from the complete ionic equation, these are considered spectator ions because they're not doing anything. Okay, that kind of wraps up our precipitation talk. Let's start talking about acid-base neutralization reactions. Remember, if we have strong acids and strong bases, these are also considered strong electrolytes. So oftentimes, acid-base neutralization reactions are also written in complete ionic equations and net ionic equations. Okay, acids and bases are going to be substances that, well, acids are going to be substances that donate protons, and then bases are going to be things that accept protons. Acids are going to be things that have pHs lower than 7. Bases are going to be things that have pHs greater than 7. And if we have an acid-base neutralization reaction, we're going to take an acid, combine it with a base, and we're going to neutralize them both. Our neutralization reactions are going to be based on the type of base. So all of our acids, we can kind of look at all the same. They're all just going to be proton donors. But our bases are going to be slightly different. So we're going to have a couple of different bases we're going to look at. We're going to look at carbonate bases, bicarbonate bases, hydroxide bases, sulfide bases, and ammonia bases. So we're going to start with the most common one, and that's going to be hydroxide bases. And that's going to be a metal cation plus a hydroxide ion or ions. So something like sodium hydroxide would be considered a hydroxide base. When a hydroxide base reacts with an acid, so we have some BOH reacting with HA, it's going to produce water and a salt. And this is going to be the same every single time. So we've got hydroxide and that hydrogen combine to produce water, and then we have our B and our A combining to produce our salt. Our net ionic here is going to be H plus OH minus goes to H2O, and generally your BA is going to be aqueous, so these are going to be spectator ions. Okay, pretty simple. If you change the charge of your B or your A from a magnitude of 1, you're going to change your balancing here. Just remember that all of your hydroxides and all of your hydrogen or H plus ions will combine to produce water, while all the B ions and A ions are going to combine to produce your salt. Okay, next we have a sulfide base. So this is going to be some, that's not what it was. Some B2S, so something in there, some cation is going to come in and be attached to a sulfur, and it's going to react with an acid to produce a gas, hydrosulfuric gas, and a salt. So there is no water evolution in this particular reaction. Okay. So here we have our hydrogens combining with our sulfur to produce our gas. And then we have our cation anion producing our salt. So again, we have an S2 minus plus 2H plus going to H2S as our kind of net ionic equation. Next are carbonate bases. So here we have some sort of base that contains a carbonate ion. So here we're going to react this with an acid. And when that reacts, we're going to produce carbon dioxide, water, and a salt. So again, here we're looking at our hydrogen combining with carbonate. And when that combines with the carbonate ion, we're going to produce water and carbon dioxide. What's left over is our salt. So our overall reaction here, our net ionic reaction, is CO3 2 minus plus 2H plus goes to CO2 plus H2O. I hope you're recognizing through this that with a net ionic, gases, liquids, and solids are going to be things that are going to stay as combined things, and it's our aqueous things that are going to break apart into ions. Okay, last one is our bicarbonate base, which is very similar to our carbonate base. We have BHCO3, so bicarbonate, reacting with an acid to produce carbon dioxide, water, and a salt. So now we have our bicarbonate reacting with our hydrogen to produce carbon dioxide and water. Everything left over is our salt. So our overall net HCO3 minus plus H plus goes to CO2 gas plus water. And I'm sorry, I have one more, and that's our ammonia base. So this is something that has a nitrogen. So it just has to have nitrogen in it. So I'm just going to go with Rn plus HCl, or sorry, HA. These are just going to combine together, and what we're going to get is RNHA. So the hydrogen's going over here, and we're making this salt. So this is, if we're looking at it as a net ionic, it would look like this. Like so, but we also have this anion that kind of just hangs out and balances charge. So all you're going to do is you're going to attach the hydrogen onto the nitrogen, and then that's going to form this charged complex, and then the anion's going to kind of hang out around it. Last thing I want to talk about, and I'm only going to very briefly talk about this, is the idea of redox. Because I'm going to go over this a little bit more in detail in class, through an example. But redox is reduction plus oxidation. So this is our last reaction type for this lecture, where reduction is the gain of electrons by an element, and oxidation is the loss of electrons by an element. So there are a bunch of steps to doing redox reactions. The first thing is determining the oxidation number or state. And this is a theoretical charge which is based on the assumption that the compound you are looking at is ionic, which is not true. It's only true half the time, right? Half of them are ionic, some of them are covalent, but we still treat it like an ionic species, and it's just a mechanism for kind of looking at our charge, or for bookkeeping the movement of electrons. Okay, now there are a lot of steps with balancing redox reactions, which is why I'm just going to go ahead and do that in class. But do have an additional video on my channel about balancing redox reactions if you want to watch a longer video on it. Okay, that is everything. I will see you guys later.